So today I'll be talking a little bit about quantum query complexity, and this is joint work with Job Briet and Carlos Paletuelos. So one of the goals in quantum computation is to understand the power and limitations of quantum algorithms. And we do know of some areas and subfields where quantum resources are known to help. For example, communication complexity, learning theory, query complexity, cryptography, non-local games. But in this talk, I'll be focusing on query complexity. In particular, I'll be talking about the classical quantum query model. Why do I look at query complexity? It's because the first two breakthroughs in quantum computing, that is Shor's polynomial time factoring algorithm and Grover's search algorithm, are essentially query algorithms. And in fact, in the query model, it captures problems for which you can show an exponential separation between the quantum and classical model. So let me dive into the query model. The central object is just a Boolean function, a function that maps n-bit strings to plus or minus 1. And the goal is to compute f of x given query access to x. So everyone knows f, but x is unknown to us, and we are allowed to make queries to x. What do I mean by a query? It's just a map. So a query takes in as input I, and it tells us xi. So we need to compute f of x, and we are allowed to make queries to x of this form. And d of f, that is the decision tree complexity, or the deterministic query complexity of f, is the minimal number of queries made on the hardest input, where the minimal is over all the algorithms that compute f. And there are other models of query complexity as well. For example, randomized query complexity, where you allow randomness in the algorithm, non-deterministic query complexity, unbounded error query complexity, and quantum query complexity. And in this talk, I'll be looking at the quantum query complexity. So quantum query is, So quantum query is just a natural generalization of the classical query. So it is just a unitary map that takes two registers, 0 and I. So when the first register is 0, nothing happens. And when the first register is 1, it is just a classical query. On input I, it gives us xi. And the reason it's defined this way is because it's just a unitary map. And a quantum query algorithm just consists of unitaries and quantum queries. So a D-query algorithm consists of D quantum queries and D unitaries, and it concludes by just outputting a bit plus or minus 1. For example, you can view such an algorithm as follows. So it begins with a unitary U0, then it applies an oracle, then it applies another U1, and then so on, and finally it concludes by returning a bit plus or minus 1. We say such an algorithm computes a Boolean function f with error at most a third if on every input x, the probability that the algorithm outputs plus or minus 1 is close to f of x. So on every x, a of x is equal to f of x with high probability, say 2/3. There are clearly many algorithms that compute f, and the quantum query complexity, as always, is the best algorithm on the hardest input. And that is a complexity measure here. And some quick algorithms that are captured in this framework are, for example, the simplest one is the OR function. So the OR function evaluates to 1 only if all the input bits are 1, and otherwise it's minus 1. And it's not too hard to see that the randomized query complexity of this is omega n, but Grover's quantum algorithm says you can solve it in square root of n queries. And if you allow partial functions, that is, the function has a domain which is strictly a subset of the n-bit strings, you can get exponential separations between randomized query complexity and the quantum query complexity. And the first such exponential, not the first, one of the exponential separations here led to Shor's polynomial time factoring algorithm. And there are other algorithms such as element distinctness, triangle finding, NAND tree evaluation, pattern matching. There's an entire quantum algorithm zoo where you could look at quantum query algorithms which give polynomial speedups. In this talk, I'll be looking at lower bounds. So I mean, for the OR function, can you do it in can you compute it in lesser than square root of n queries? And in the direction of lower bounds, there are two extremely well-known methods, the polynomial method and the adversary method. And the polynomial method translates lower bounding quantum query complexity to something purely algebraic called the approximate degree of a Boolean function. So the approximate degree of a Boolean function is defined as follows. You look at the minimal degree of a polynomial, that is firstly n-variate, and that approximates a Boolean function, that is on every x, p of x minus f of x is close to a third, and p is just a bounded polynomial. So this is the approximate degree of a Boolean function. And the polynomial method by Buell et al. In 1998 showed that the quantum query complexity is lower bounded by the approximate degree of a Boolean function. So it translates lower bounding quantum query complexity to something purely algebraic, that is just understanding the approximate degree of a Boolean function. And using this method, they reproved the search lower bound. That is, they showed that square root of n queries are necessary to compute the OR function. And this was also used in the collision finding and many other algorithms to prove lower bounds. Along the same time, there was another method called the adversary method that was introduced by Ambainis. And he introduced the positive weight adversary method, which lower bounds quantum query complexity. It came about the same time as the polynomial method. And eventually, it was generalized to negative weight adversary method. And Reitkart et al. In 2011, after a sequence of works, showed that the quantum query complexity is theta of the negative weight adversary method. So just computing the quantity given by the negative weight adversary method tells you the quantum query complexity of a Boolean function. And because it's a theta, people also used it to construct many new algorithms using this negative weight adversary method. The question that I'm trying to understand in this talk is, can we say a similar theta kind of statement about polynomial method? Does the polynomial method also give you admit a converse? And the first natural question one can ask is approximate degree of a Boolean function theta of quantum query complexity? And the answer is no. So Ambainis gave a function for which there's a polynomial separation between the approximate degree of a Boolean function and the quantum query complexity. And there were some works in this direction, but Aronson and Ambainis defined a new measure called the block multilinear approximate degree. And this used a lot of structure of quantum query algorithms. And in particular, what they showed was it sits between approximate degree and quantum query complexity up to some constant factors. And because it used the structure of quantum query algorithms, something they naturally conjectured was it's a block multilinear degree, theta of quantum query complexity. And the answer to this as well is no. In a subsequent paper, Aronson et al. Showed a specific Boolean function for which there's a polynomial separation, a quadratic separation even, between block multilinear degree and quantum query complexity. And so there are two natural questions to ask. Is there a refinement of approximate degree that characterizes quantum query complexity? And the second one is, so most of these separations were for polynomials which are non-constant degree. But let's just say we look at degree 2 or degree 4 polynomials. Can you get quantum algorithms from them? And the first contribution in this paper is we give a positive answer to the first question. We give a new degree measure that characterizes quantum query complexity. And we call it the completely bounded approximate degree. So let me define this measure first. So let f be a total or a partial function. That is, it could be defined on the entire Boolean cube or on a strict subset even. And let epsilon be a number between 0 and 1. The CB-deg, or the completely bounded approximate degree, is the minimal degree of a polynomial p that is 2n variate. This 2n is not really important right now. And it's a good approximator for f. What does that mean? So p is defined on 2n variables. Let's just fix the last n variables to all one string. And on the first n variables, I'm just going to let it be x. In that case, p of x comma 1 to the n minus f of x is at most 2 epsilon. So it's a good approximator to f on the defined domain of f. And the most crucial thing was p is not just bounded, but it's completely bounded. So that is a new additional constraint that we are placing on this degree measure. And I'll define in the next slide, I'll give you an intuition of what the completely bounded means, but the main theorem is the following. Suppose you have a Boolean function, partial or total, for which epsilon is either 0, anything between 0 and 1. We have that the completely bounded approximate degree is equal to the quantum query complexity. There are no constant factors or anything, it's just a pure equality. So we give a complete characterization of quantum query algorithms in terms of this degree measure, and that also gives us a converse to the polynomial method. And the proof of this theorem actually comes from the following characterization of quantum algorithms as such. So let beta just be a map that takes n-bit strings to something, a number between -1 and 1, and let d just be a positive integer. Then the following two statements are equivalent. There exists a 2n variate polynomial, which is homogeneous. A form just means a homogeneous polynomial of degree 2d, so that p is completely bounded. And p evaluated on the inputs x comma 1 to the n is equal to beta of x. This is equivalent to there existing a quantum algorithm that makes d queries. and that on input x returns a sign plus or minus 1, and the expectation of the sign is equal to beta of x. So this is our main characterization result. And the proof of this goes through a seminal result of Christensen and Sinclair back in the 80s. And this concerns multilinear forms on C-star algebras. And this was a very nice factorization theorem of completely bounded forms. So I'm not going to define what is this completely bounded number for polynomial, but I'll tell you what this actually is, what this quantity looks like. So let's just look at a tensor T. It's a D, let it just be a D-linear form. And we say T is bounded if supposing this quantity is satisfied. You take the maximization over all n-bit strings and take D of them. And if you evaluate the polynomial on these, on x1 to xd, and this quantity is at most 1, we say T is bounded. And what I mean by completely bounded is I'm going to replace these bit strings x1 to xd by unitary sequences. So T is completely bounded if I replace x1 by unitary sequence and xd by unitary sequence, and I maximize over all possible dimensions of these unitaries. And instead of the absolute value, I just look at the operator norm. So that's a natural generalization of being bounded. And this notion of completely bounded sort of characterizes how quantum algorithms look like. I mean, if a polynomial is completely bounded in the following way, then there exists also a quantum algorithm. So let me look at the second question that I asked earlier. The constant degree polynomials characterize constant query algorithms. So let me first define what do I mean by this question. So in the original paper by Beals et al. That introduced the polynomial method, the key theorem that they proved was the following. Suppose you have a D-query quantum algorithm that computes a Boolean function f with error at most epsilon, say. Then it induces a polynomial which is degree 2D and n-variate, and that satisfies, and it is close to f of x on the f on the Boolean cube. That is p of x minus f of x is at most 2 epsilon. So a way to view this is D-query quantum algorithms give you degree 2D polynomials. And the second question that I ask here is, can we go the other way around? Can I start with a polynomial, and can I get a quantum algorithm out of it? And in this direction, Aronson et al. Proved that it is actually true for D equals to 1, though. That might seem very simple, but the point is it was a very beautiful result where they showed the following. There exists a universal constant C that depends on the Grothendieck constant. And so that if you give me a degree 2 bounded polynomial, then there exists a one-query quantum algorithm that on input x, it returns a sign plus or minus 1. And the expected value of this sign is actually equal to the polynomial evaluated on x divided by this universal constant C. And this was an extremely long proof, and the first contribution in this paper was we gave a simple one-slide proof of this thing, but I'm not going to talk about the proof of this. But crucially, what's more important is because we had the simple approach, we showed that the second question that I asked right on top is actually not true for when you begin with degree 4 polynomials. That is to say that if you give me a degree 4 polynomial, you cannot hope to have a quantum algorithm which makes 2 queries and that returns a sign plus or minus 1, which has expectation exactly this degree 4 polynomial evaluated on x divided by some universal constant. So we kind of give a negative, so that was an open question in Aronson et al.'s paper, and we give a negative answer to it for D equals to 2 already. So let me give a quick summary of our results. So the motivating question was, does the polynomial method admit a converse? And our first answer was yes. We gave a new degree measure that characterizes quantum query complexity even up to constant factors. And the second thing is we show that if you start with a degree 4 polynomial, you cannot hope to have a 2-query quantum algorithm that computes this polynomial in expectation. And some directions for future work. So let me give you some historical context here. So there was first this polynomial method, and then there was this adversary method. And this adversary method was strengthened to the negative weight adversary method, and it was eventually shown to characterize quantum query complexity. And because of this characterization, people came up with way too many new algorithms because of this negative weight adversary method. And what we have shown now is the polynomial method can also be used to give upper bounds on quantum query complexity. Can we use this to construct new quantum algorithms? And secondly, the crux of our theorem actually came from a very old result in operator space theory. And it'll be interesting if we can actually use results from operator space theory to either give new lower bounds or better upper bounds for quantum query complexity. With that, I thank you for your attention. Actually, that's an open question in operator space theory. So there exists a semi-definite program to compute the quantum query complexity, but and we were trying to use this to actually give a maybe polynomial in 2 to the n algorithm for deciding the completely boundedness, but there are some subtleties there. But it's an open question, though, what you ask.
How do you explain this amazing coincidence that this concept in operator space theory is computational? It captures precisely the complexity of.
I think it's just coincidence, actually.
Yeah. So it's remarkable.
Yeah. More of it's very obscure. Just by looking at the theorem statement, it's not at all, because it's phrased in terms of C-star algebra, so it's not clear that you can get a quantum algorithm from it.